Well, hello everyone, and welcome to Thursday Night Calculus. We are doing a session tonight. Zeros are my heroes. I'm really excited to be hanging out with these folks who are definitely not zeros. I'm joined by Vicky Carter and Tom Dick, Steve Kokoska. Once again, I'm really excited to have them here and sharing their expertise with us. And so I won't take up too much time, but I do have one little thing to make sure that I announce, and that is that teachers, for sure, if you stick around towards the very end, I will be sharing my email address. You can snag that from the chat and then email me for a professional development certificate. I'll take care of that. But otherwise, if you're wanting to follow along, Steve has posted the questions down in the description of this YouTube video, so you can go there and download those and get started. All right, Steve,
Thank you,
take it away.
Curtis. Thank you very much. Great to be with all of you again this evening. Indeed, tonight, Curtis, we're going to talk about analyzing polynomial graphs. And yeah, there'll be some zeros in there. We think that these questions that we've given you this evening are very typical of what a student might find on the AP pre-calculus exam. Most of these, I think, are just kind of expanded multiple choice questions, although the one at the very end, if we get to it, could be a free response. I want to emphasize again, Curtis, that we do encourage questions. So I know if you're monitoring the chat, please feel free to interrupt at any time. And Tom and Vicky will chime in, and Tom will do some technology. And here we go. Let's see what we can do with some of these. So this very first problem deals with a polynomial function p, and it's given here already in factored form. So I actually did a little bit more in the beginning of this problem than one might see. We want to find all the intervals in which p of x is greater than or equal to 0. And I guess one of the very first things that I would do here is to make sure that this polynomial is in completely factored form. And what does that mean? It's factored into products of distinct linear terms and irreducible polynomials, irreducible quadratics, excuse me. So Curtis, here's a question for tonight. What the heck is an irreducible quadratic? Let's see if we can get an answer to that one. So how do you solve this? This is already in completely factored form, and I'll show you how I do some of this, and you may have a better way, Vicky or Tom. Here's this polynomial in completely factored form, and you'll notice that one thing I did, and I learned this many years ago, was I put the distinct linear factors sort of in order of their zeros. In other words, the three zeros here are -3, 2, and 5, and you'll notice that the linear factors here, there's the one that corresponds to -3, there's the one that corresponds to 2, and there's the one that corresponds to 5. So in my weird way of doing things, I like to write them in that order because it's going to make it a little bit easier for me as I do my analysis. Now, there's lots of different ways to analyze this and to come up with this answer. One way is to write this kind of a nice chart where we write these intervals over here. Now, how did I get those intervals? Well, those intervals are determined by the zeros of this polynomial. So the zeros of the polynomial divide the real number line up into intervals. And it might even be easier to see by looking at my sign chart here, which I'll look at again in more detail in a minute. But I drew a sign chart. It doesn't have to be drawn to scale, but I tried to do a little bit of that with -3, my zeros, -3, 2, and 5. And it's a little bit clearer, or I can see graphically or visually what my intervals are. -infinity to -3, -3 to 2, and so forth. Now, some people even add a little bit more here in this interval column. Some people will even add an extra row here, for example, where they say x is equal to 3, or x is equal to 2, or x is equal to 5. I don't think that's necessary here. I'm looking for where my polynomial is positive or negative. Okay, so now what I need to do is to determine the sign of each one of these linear factors, and then put all of that together to determine the sign of my polynomial. Well, I can do this by arguing in general or by picking a specific value in this interval, minus infinity to minus 3. So here's how I might do that arguing in general. If I take a number to the left of minus 3, notice that this term would be negative, this term would be negative, and so would this. And oh, don't forget that lonely negative sign out in front. So I put all of that together, and my polynomial is positive. So I cross over minus 3, and I look at the interval minus 3 to 2. Again, I could take a specific value in there, like a nice easy one might be 0. But for me, I know with these linear terms, as I cross over minus 3, this term now becomes positive. And so if I look up here, I have 3 negative signs. Okay, so my polynomial is negative. Now I cross over 2, this linear factor becomes positive. Multiply across, well, let's see, I've got 2 negative signs there, so the polynomial is positive. And finally, cross over 5, take a number bigger than 5 in that interval 5 to infinity. And all 3 of these terms are positive, but I've still got that negative sign out in front. And so the polynomial is negative. So one way to attack this is by taking a look at a chart like this. But again, another way to look at this is by drawing a sign chart. Tom and Vicky know that I'm a big advocate of sign charts, and I was very sad to see these disappear from the AP Calculus exam, but maybe they'll come back at some point. Students can still use a sign chart, but on the calculus exam, they're not sufficient justification. Now, we don't see justification asked for in this problem. We're thinking about this as a multiple choice question. So sure, a student could use a sign chart. How do you do that? Well, you draw a number line and you put tick marks in here for the zeros of the linear terms. That divides up the number line into, this case, 4 separate intervals. And now I argue similarly as above. If I take a number over here to the left of minus 3, I know that all 3 terms here are negative. I've got a negative sign out in front, and I know that P of X in this row is positive.
Hey, Steve,
Yes, sir.
we did just get a nice question in the chat. Are there
Good.
cases where a sign chart cannot be used to determine end behavior?
Determine end behavior. What do you mean by end behavior? Whether it's going off to plus infinity or minus infinity?
I'm going to make the assumption that that's the question. Whether or not it's headed off to a particular, infinity might be a reasonable question there. Yeah.
Okay, so that's a good question. If it is a polynomial, not a rational function or anything like that, certainly a sign chart could be used to determine end behavior, but that might be overkill. So
That's fair.
generally, if we have a polynomial and we're just asking about end behavior, we can generally do that by taking a look at the term with the highest power and the coefficient on that term. So we don't generally have to take a look at a sign chart. Now, if we're using the sign chart for this other information, like what do we ask for here, where P of X is greater than or equal to 0, sure, we can read off this and we know from this sign chart that as X goes to minus infinity or as X decreases out without bound, we know that this polynomial would increase without bound because of that positive. And we know out here to the left, to the right of 5, if X increases without bound, we know that the polynomial is decreasing without bound. So yes, it can be used, but probably overkill. Okay?
Steve,
That was a good
yeah,
question. Yeah.
yeah, I think that's an excellent question. The fact that we started with a factored form
Yep.
may be a reason to perhaps consider the sign chart.
Mhm.
Otherwise, the students are going to have to do some kind of thinking about, well, if I expanded that, I don't want to really have to totally expand it. But think about what's going to happen with that expansion and then what the end behavior would be.
Good.
So while we're on this,
Yes.
I think just in general, working with students for many, many years, Some students handle a sign chart very well. It makes sense to them. They understand
Yep.
what to do. Some students will write the little values that they sort of thought about substituting into the factors, maybe in the little intervals or below it or something like that. But other students need a little more foundation in what they're trying to do. And in that case, some form of that table might be what you want to do with some students in order to help them with this, finding out when something's positive or negative, in this case, the inequality, and just give them a helping hand if that sign chart is not clicking for them.
That's a
So,
really nice point, Vicky.
so Curtis, after all of this, let's finally answer the question if we
Yeah,
can.
let's do that.
Oh, well, you asked a question. Maybe we ought to answer it.
Let's put all of this together and we were asked, where is the polynomial greater than or equal to 0? And looking at my sign chart, looking at the chart up above, here are the two intervals. And Curtis, did we get an answer yet to an irreducible quadratic?
No, we've not gotten an answer to
Oh my goodness. So
reducible
does that mean
quadratic.
we win the car tonight?
I think I'm going to take it home.
Okay. Well, here's another question, okay? Well, remember, now those of you who also teach AP Calculus, this is an AP pre-calculus question. I wonder why these are closed intervals here and not open. And we'll leave that as a question. And let me arrow up a little bit more here if I can. See if I can get this to work. How about that? Tom knows I always like to do this. I kind of like to back up my answers, my analytical answers with a graph. This one I created with Mathematica, although I'll do a lot with the TI-Nspire in a bit. But there's a graph of this polynomial. It does, in fact, confirm the end behavior that we talked about a minute ago. And you can also see here where this polynomial is positive or greater than or equal to 0 over here to the left of -3 and in here between 2 and 5. So good graphical confirmation of what we just went through analytically. Very
Hey,
good.
Curtis, did we get an answer on the irreducible quadratic?
Not yet.
Oh
Oh no,
no. How
that's
about
still
the
pending. Are you going to give out the secret there, Steve?
oh no answers yet? No, no, no. This is an hour-long show, Vicky.
Can't
How
be giving
about
answers this soon.
We
how about
can't give the answer just yet. No.
the square bracket, Curtis, over here? We got an answer there yet?
I haven't seen one in the
Okay.
chat. No. Mm-mm.
Tom, should I look at number 2 first before you do any technology?
Um, Actually, Steve, this might be a good one to look at a little bit of technology.
All right.
Bear
Deal.
with me. Okay.
All right, I'll stop sharing. There you go.
All right. I'll see if I can share.
So I did get one answer from Miss Connor, who has several students actually in here, and that is that p of x greater than 0 means positive, as in the function is above the x-axis, not just on it. Just further explanation for my kids. Square bracket because it is greater than or equal to 0.
Very good.
Very
Excellent.
important.
Okay, so we do have to
That's
pay
nice.
attention to those details. Very good.
Nice
Excellent.
responses there. Thank you, folks, for doing that. Still looking for the solution there on this irreducible, though.
Oh, no. Okay.
I'm scrolling and I don't see it yet. Maybe I missed it.
Okay. All right, Tom. Sorry.
Oh, no problem. Well, I'm going to hope you're seeing my TI-84 screen.
We do indeed.
Going to jump into the Y1 or Y equals menu here and enter that function that Steve was talking about. So it was negative. Let's see, and we had it in factored form. I think we've got x plus 3 times quantity x minus 2 and times x minus 5.
Right.
And I should have called attention to this, but that leading negative sign out here front, you can notice that it actually looks different than the subtraction signs that are showing up here. And that is a separate key. It's something that new calculator users sometimes trip up on, is the negation of number. That's a technical term, it's a unary operation as instead of subtraction is a binary operation. It's actually got a little bit different symbol to it. And so if you put in a minus, an actual subtraction sign here, you get kind of an error. So that's something to keep in mind. So I'm just going to go ahead and graph this in a zoom decimal window. And Steve's scaling on this was a little nicer. It actually showed the max and mins of this graph. But for the time being, let me go ahead and stick with this. Actually, I will go ahead and change the window a little bit. So let me go ahead and make my Y min negative 100 to 100 for Y max. I think that's approximately what Steve had on his nice graph. So if we graph this again, there we go. All right, so there's a graph similar to what Steve had.
Yep.
And this corroborated Steve's analysis with the sign chart. I did want to show another, since we're looking at inequality, that there is actually a way to plot an inequality on the TI-84. And so what I'm going to go is go back to my Y equals menu. I'm going to go to Y2, and I kind of like to use parentheses on here. This is going to look kind of weird, but I'm going to put in Y2. I'm going to go to my variables menu, pick up the Y variables, function Y1, and I'm going to put in the inequality Y1 greater than or equal to 0. Okay, so I'll need a greater than or equal sign. I'll go to the test menu. That's a shift of the math menu. I see it down there, number 4. Oops, overshot. There we go. Y1 greater than or equal to 0. And the question is, what in the world? That looks very strange symbolic. I do really think of the Y1, Y2. Those are labels. These are labels for things I'm going to plot. And when you put in an inequality in your Y equals menu, it's treating this as, well, okay, I'm going to plug in each value of X and then just check and see if this is true or not. If it's true, I'm going to plot the value 1. If it's false, I'll plot the value 0. So this should be equal to 1 wherever this is true, 0 wherever it's false. So let me go ahead and graph. Really hard to tell here because of that scaling. So I'm going to actually go back to my zoom decimal scaling again. Number 4. And you can see that where this is equal to 1, this is 1 on the intervals of which that Y1 function is positive, greater than or equal to 0.
Mm-hmm.
It's 0 where it's not, okay? And so we're getting, again, a different kind of corroboration of those intervals. I just wanted, I think that type of inequality truth plotting, I sometimes think of it as, because it plots 1 for true, 0 for false, is sometimes not everyone is up to aware that you can plot in that way.
So Tom,
Yeah.
I think this is actually a very powerful graph for students to see. I've so many times run into students who can't actually visualize what Y greater than 0, Y less than 0 means. I mean, they understand, but they can't think about it graphically. So this connection, oh, Y greater than 0 means it's above the x-axis, and Y less than 0, the points are below the x-axis. But I think this sort of summarizes it very nicely for those graphical students that need to see it.
Mm-hmm. Right.
Tom, I have a question about this. I don't want you to do this now, but in order to make it more visual, as Vicky says, it would be kind of cool if where the polynomial is positive, the horizontal line is positive, as it is, but where it's negative, the horizontal line is indeed negative, not on the x-axis. So I'm sure there's a way to write some piecewise defined function so that that occurs, so that it's 1 where it's positive and -1 where it's negative, but we'll leave that as an open question for next time, okay?
And My thought was to take it one step further and just do that inequality in y2 that he had and multiply by y1. And then just you would only see,
Oh,
you could take y1 and divide by that inequality, and you would
sure,
only see the positive portions, the above the
sure.
zero portions. Um,
And
Oh, I see. It would only show the
yeah.
parts of the
it
graph.
would only show the parts of the
Yeah.
graph that were positive.
Yeah.
And Tom, there was one other thing in the previous calculator graph screen that you showed. I don't want you to go back to that, but I just wanted you to comment on this because a lot of people see this, but they don't know what's going on. If you remember when you had that graph up a minute ago, the vertical axis or the y-axis was almost boldface. It was
Mhm.
thicker than the x-axis. So maybe you could just explain that to people because, that would happen. You'd say, "Oh my gosh, what's going on here?"
Right. Well, I'll just bring up the window,
Okay.
and the X scale and Y scale, that determines where those little tick marks or hash marks are on the axes.
Yep.
And I didn't change those when I used the negative 100 to 100. So
Okay.
it was still giving me a little hash mark at every 1 unit. Well, that just basically ended up looking like solid hash marks because they're
Gotcha.
so that's exactly what was happening.
Gotcha.
One
Okay.
other point I was going to make, that it's actually relevant both to your analysis, Steve, and
Yes.
what's going on here graphically. Graphically, this is only showing me what happens between like negative 6 points, x equal negative 6.6 and x equals 6.6. How do I know that the graph doesn't turn around and cross, become positive, negative at other stretches outside of my window?
Mm-hmm.
And as far as your analysis is, why does your table stop with just to the right of the last zero and to the left of the first zero? And the point of the matter is polynomials, they're continuous. So once you don't have any more zeros than you have the degree.
Yep.
We have all the zeros accounted for here. So there's no way this can cross outside of what we're seeing here again. So where this has become negative, and it relates into your end behavior analysis.
Sure.
I know that this is negative from here on out. From all x's greater than 5 are going to make my function values negative. And over here, all the values to the left of -3 are going to give me positive values because we've got our 3 zeros staring at us. We can't have anything else. So, but that's using what we know about special properties of polynomials. We know that they're nice and continuous, and we know that there aren't any more zeros than the degree of our polynomial. So, all right, I want to turn it back
Pretty
over.
good. Okay. Curtis, we're going to try problem number 2. Okay with you?
I think that sounds great.
Okay, here we go. All right, I like this one. Here we have a function f, which is a 4th degree polynomial, and it's got a couple of decimal coefficients in there. And we want to do several things here. We'd like to find all the real zeros of f, and we want to talk about the behavior of the graph of f near 0, and see if we can explain why that behavior is occurring. We want to find all the values of x such that f of x is equal to -10, and you're kind of getting the idea here that this is a calculator active question. And finally, in D, we want to use technology to sketch a complete graph. Tom and Vicky helped me here a little bit, but this has always been, since the inception of the use of calculators, this has been one of the 4 uses that was required, right? Be able to sketch a complete graph in an appropriate viewing window. And yet, for the life of me, I don't think I can ever remember a question that said, had you do something like that? I mean, how could you even ask that? But it was like, we need to be able to get a complete graph. What is that? Well, to
Well,
me,
Steve, it kind of does go back to number 1 when Tom
yes,
changed the Y min and the Y max, because we weren't really seeing a complete graph with that zoom decimal,
that is correct.
or at least that's my kind of thinking. So keep going.
Yeah, well, I mean, I can't remember a a question that really required a student to do this in the AP Calculus.
But if they couldn't do it, they might not be able to answer some other question.
That is correct. That is correct. Yep, some other part. Yep. So we're going to try to do that here. Okay. So here we go with part A. Find all the real zeros of f. I'm going to take 1 second in here and see if I can scroll up a little bit. Here we go. Now, some of my calculator screens, or most of my calculator screens, will be of the TI-Nspire. I enjoy using that. I won't go through all of the keystrokes in order to get my answers here, but Tom may show you a little bit with the TI-84, some equivalent built-in commands. And I think if you see some of these results on the Inspire, you may find yourself saying, boy, I'd like to use that machine. I really do enjoy it. So the very first thing I'm going to do is when I took a look at this function, this polynomial, I noticed that I could factor out an x squared out of each one of those terms. So there we go. I factored out an x squared. In doing so, I know immediately that x equals 0 is a 0 of this function. All right, well, I don't know. How am I going to find the zeros of that quadratic? I guess if I really wanted to, I could use the quadratic formula. But you know what? We're going to use technology to do this. We're going to do it in a couple of different ways. So the first thing I did with my TI-Nspire is I defined a function f, and that's the way you would do this on an Inspire. It's pretty intuitive. And then I'm going to use the built-in command called zeros. Does exactly what you think. It finds the zeros of that function f where x is the variable. And Tom knows, I don't know, Vicky, if we've talked about this, but Tom knows the reason that I like to use this command is because when the Inspire finds these answers, it puts them in a list. It puts them in a list so that I can extract any one of those values and use it in another calculation. So it is stored, found and stored to a great degree of accuracy, and then I can extract any one of those values. So as an example, what I did is I used the command zeros and I stored that in a variable, a list variable that I call the z. And then if I want the very first value in that list, I can just use, the way that I say that is z sub 1. That 1 is like a subscript to me. And it comes back and tells me, well, the value in that list was minus 3.1. I think that's pretty cool. So just thinking ahead, I might want to find these zeros and I might need to use them in a further calculation. They might be more complicated. They might have more digits to the right of the decimal. I can find them to the greatest degree of accuracy allowed by the calculator, and then I can refer to them. That's neat. Now, that's one way to find them, and I think I found all three of them. Minus 3.1 and 12.3. Hey, wait a minute. This is a fourth degree polynomial, but I've only got 3 there. Well, wait a minute. That's because 0 is a repeated root or a repeated 0. There is another way to do this, and I know that a lot of students like to find these zeros in this manner. I've graphed this function f in a window from if you can see this, Curtis, minus 10 to 15. And this is minus 6.67 to 6.67. Now, I can't really tell what this polynomial or what this function looks like. I can see some of it on the graph screen or on this graph window. And I can see enough of it around, of course, the x-axis so that I can use the built-in zero function on the graph menu. And so doing that, I found these 3 points, minus 3.1. Oh, there's the origin. It goes through the origin, 0, 0, and 12.30. So there are 2 ways to do this. I tend to prefer the more analytical one over here on the left-hand side. Many people prefer the more graphical one on the right-hand side.
So
Fortunately,
Steve, all right, but let's talk about something that students will do.
yes,
So that they have a very bad habit of doing a standard window.
yes,
Okay. So they look at Zoom standard
yep,
and which goes for your X min is negative 10 and your X max is positive 10. And
correct.
it is a proportional window. So 1 unit tick marks on the X axis is the same distance as 1 on the Y axis. And if they are playing the game of seeing is believing, they may think that this function only has 2 zeros because
Yeah.
they would not have found that 12.3.
Yep,
So
they
this is again part of that looking for a complete graph and understanding what a fourth degree polynomial should be doing in order to adjust the window in the way that you did.
Yeah, and I would argue that part of this is noticing that that is a fourth degree polynomial, noticing that there can be up to 4 roots, 4 zeros. And if I've only got 0 as a repeated root, and I've got the minus 3.1, boy, there better be another one somewhere. And that better be a clue to try a different window.
Yes.
Yep, absolutely. Okay, Curtis, sorry. It's the answer to part A. There are my zeros down there, minus 3.1, 0, and 12.3. Okay, so what the heck was part B here? Explain the behavior of the graph of f near 0. Okay, so what's going on there? Well, at x equals 0 is a 0 of the polynomial function with multiplicity 2. So the signs of the output values are the same for the input values near x equals 0. That means on the same side. So on either side of 0, the sign's got to be the same. They're either both positive or they're both negative. Now I'm going to cheat a little bit. I'm looking at my graph up there. I'm not sure if I could tell in another way, but you can see that they're both negative. Okay. Now, I don't know, Vicky, help me on this one a little bit. Can I also say that the graph of f is tangent to the x-axis at x equals 0? Is that something
Yes.
we might
That
learn about?
that honestly is my preference, but I hear a lot of descriptions by both students and teachers, excuse me,
Yeah.
that the
Well,
curve bounces on the x-axis.
I'm not sure I like that one, but
Yeah,
okay.
I don't either. I mean, I get it. It's like a ball upside down, you know, it hit the ceiling and it comes back down.
Okay.
You know, but if that's the visual and the explanation that students need, you know,
Okay.
so be it. But it's not what I would write down. It might be just what I say in the classroom, like to try to describe the phenomena of what's happening near x equals 0. But my preference is to say that it's tangent to the
So,
x-axis.
so Vicky, at this point, students in pre-calc would only have sort of an intuitive idea of what a tangent line to a curve is, sort of
Yes.
touching that curve right at that point and headed in the same direction as
Hmm.
that curve is about the best that we can do.
And I think so, but I
Yeah.
think it gives them an understanding of what these zeros with even multiplicities are going to do. And they
Okay.
do need that understanding, both graphically and looking at the factors of the polynomial, you know, what happened with that x squared. So they've got to kind of be versatile with both the analytic, you know, the graphical and things like that.
Okay. All right. Let's take a look at part C. In part C, we were asked to solve this expression, I think it was, f of x is equal to minus 10. Well, I can do that very quickly on my TI-Nspire. Remember that I already have this function f defined. And so I'm going to find, actually, I'm going to rewrite this a little bit. I'm going to write this as f of x plus 10 equals 0. I'm actually going to find the zeros of that expression on the left-hand side. Okay, yes, there's a solve feature. There's a solve function, excuse me. But once again, I like that zeros function because it will put all of my answers into a list in the event that I might need them later. Now, I think what's kind of cool here is that when I asked for the zeros of this, it came back with, I hope, all 4 values. It came back with 4 answers, and I believe that that is it. There aren't any others. That's an exhaustive list. I'm going to double check that. I'm going to look at it graphically over here on the right-hand side, and here is a way to do it. I don't know if you can see any color on here, but this curve right here is a graph of f. I think when I did this, that was in blue. And this horizontal line right here is a graph of y equal minus 10. When I did this, that was in green. And then what I did was I used 4 applications of the built-in intersection function. Where do those 2 curves intersect? So I did that 4 times, and I think I found the same values. There's minus 3.03 rounded a little bit. There's the minus 0.553. Okay, looking good. There's the 0.486, and there's the 12.1296. Now, here's a question. Maybe we'll leave this as sort of an open one. How do I know that there aren't any other values? How can I be sure that there aren't any other values of x such that f of x is equal to minus 10? I'll kind of leave that as an open question for a minute or two. And down in D, I think, what did I ask for? Oh, yes, a complete graph. Now, how do you do this? What's the technique to do this? Well, I know a little bit about this graph because it is a polynomial. It's a fourth degree polynomial. We talked in question number 1 about n behavior. And let's see, there was an x to the fourth, and the coefficient on that x to the fourth, I believe, was 1. So I know the n behavior here. As x increases, as x decreases without bound. And so I'm not sure if there's a more systematic way to do this than to think about what the n behavior might be, and then to simply work with the window until you see this quote-unquote complete graph. How do I know that this one is complete? Well, I know the end behavior out here is that this goes off to plus infinity and plus infinity. So there's no other feature where this graph is going to come a curve down again towards the x-axis or towards the horizontal axis. And I think I've captured everything below the x-axis. And notice I had to go down to, is that minus 3,500 in order to see this complete graph. That's pretty cool.
But you can also still see the feature of the 3 x-intercepts that we have, as well as
Yeah.
that bounce tangent to the x-axis at x
0.
equals 0. So
Mhm.
you've got it's kind of squishy there, it's a little hard to see,
Yeah.
but you do have a full graph with the features that we kind of want to see.
Yep, very cool. Tom, a little technology here?
Sure, sounds good.
Okay. There you are.
Okay. So let me share my screen again. I'll get my.
While Tom is getting ready to share his screen, I'll just point out that we did finally have somebody answer the irreducible quadratic.
Okay.
Talking about how it cannot be, what was the wording he used, or this person used, said it cannot be factored or solved for real roots, real solutions, real rational roots.
Okay. Cannot be factored over the real numbers. Very good.
Yeah.
Very good.
And they gave an example as well, x squared plus 4.
Good.
Very good.
I like that one. Very good. Tom, you've got your 84 up again.
All right. And I took the liberty of going ahead and entering into y1, that polynomial that we were looking at. And just to kind of reiterate a point that Vicky made, she mentioned the zoom standard window where you would likely miss one of the zeros here. My favorite window, people who know me, is decimal. That's going to suffer from a similar fate, I think. Okay, yeah. So I see this 0 just to the left of -3. Looks like that double 0 at or multiplicity 2 at 0, but I'm not seeing that 1 at 12.3 because it's off the screen.
Yep.
So this is one where we'd have to play with the window a bit. Let me go ahead and jump to one that'll have all the features like Steve's did. I'll go ahead and make the X-min and X-max, let's say -5 and 15. And then Y-min, Y-max, we really had to work a bit to get that. Let's see, I think, did you go down to about -3,500, Steve?
Yeah, I did, Tom.
Okay,
Yeah.
well, let me mimic you here. But I'm also going to make another change. Let's see, besides the Y-max, what was it, about 500?
Let me
I
see.
think
I've
so.
forgotten.
All
Yeah.
right. And so I'm going to
Yes.
make my Y scale, I'm going to actually make it 250.
Okay.
So what that means is there's going to be a little hash mark every 250, okay, on the y-axis. On the x-axis, I'm still going to have a little hash mark every 1 unit. So let's do a graph and see what we get.
It's thinking.
So notice that each one of these hash marks on the y-axis is actually 250. So I'm not getting that super solid behavior that we saw on that previous one.
Yep.
So on a graph like this, we could do things like zeros and actually calculate them on the graph. So I'm going to bring up the calculate menu. There's 0 right there. So let me do number 2. Let me get this first one over there near -3. Yeah, I'm a little bit to the left of it, so I'll enter that as left bound. Then I'll go a little bit to the right of it. And that's close enough for a guess. There it is at -3.1. Now that I've got that -3.1 there, I'm actually going to quit from the graph screen.
Good.
And I'm going to pull up that X value. There it is. So the last X value is this one that we calculated as a 0. So I'm going to put that away for safekeeping. Let me store that in A. Okay. And then I'll go back to the graph, hit calculate again. And, you know, I already know that one of the, I'm going to save a little bit of time here. I know we've got a double 0 at 0.
Mm-hmm.
Okay. So let me just go ahead and get to the others one, which is around, well, it looks like it's between 12 and 13 there. And I realize we've already seen what that value is, but just kind of demonstrate how this works. So I'm going to go.
As you're tracing across there, Tom, can you type in a left bound if you wanted to?
Yeah, I think so. Let me
Okay.
try that. Let me put in 11. Yeah, there it is. So there's
Okay.
my left bound, and let's see. Let me put in 13
Okay.
for the right bound. Great. Yeah, thanks for suggesting that or asking that. And then for a guess, well, 12 is kind of in between. Let me put 12 in as a guess.
Okay.
And boom, it zooms in. I mean, these really actually had pretty decent, nice, I'll call them nice values for your zeros. It was only to the 10th place. But there's that 12.3. And so let me go quit again, bring up that value of X. There it is, 12.3. Let me store that in B. And then I'm also going to store 0 in C.
Okay.
And I'm going to store 0 again in D.
Uh-oh.
Because it's a double multiplicity 2 root. So let me give it 2 separate labels here.
Okay.
Whoops, I didn't want to do that.
Yeah, that might be dangerous.
Okay. All right, let's try that all over again. So 0 store alpha D. There we go. Didn't quite hit my alpha thing. Okay, so we've got A, B, C, and D are the 4 zeros, counting multiplicities, of my polynomial. So the other thing I'd like to show, if I can, Steve, is just I think it's an app that's just wonderful for working with polynomial and rational functions in particular. It's also fantastic for logarithms, exponentials, sinusoidal, whatever. But let's take a look at this. So this app, I'm going to this key that says apps. And I'll scroll down. We see all kinds of specially named things here. Keep scrolling. And there it is. It's called Transform. That's the abbreviation for it. And let me enter that. And we get this screen here. It says for animated graphing, but the thing I value this the most for is it lets you do something akin to sliders. Sliders, different graphing programs have them. Certainly TI-Nspire has them. For the TI-84, this is pretty much gives you sliders. So let's take a look at what this looks like. Let me go to my y equals menu. Oops, let's see. There we go. And if you look real close, you see that function we were playing with before, but you'll notice to the left of y1 and y2, there's a little bit different looking symbol. That's because these two particular slots for functions are set up for this transformation app and where you can have parameters. Okay. So I'm going to go down to y2, and I'm going to enter a general quadratic, excuse me, not a general quadratic, and actually, I guess it'd be a quartic would be the technical term, but fourth degree. Yeah, fourth degree polynomial that's in fully factored form where the roots are just called A, B, C, and D. So I've got x minus A times x minus C, or x minus B, I should say, times x minus C, and then finally times x minus D. Okay, so that's a fully factored, but this A, B, C, and D, these are values that we can manipulate in the transform app. Okay. Now, they actually have values already. You can guess what the values are. They're the ones we just stored away.
Yeah.
So
our zeros.
So if I graph this, if it happened pretty quick, but you saw the blue graph, that's the original we were working with. Notice that this red graph lies right on top of it, but down at the bottom, you see that A, B, C, and D are all labeled there. And now these are manipulable. I can actually change these values. So what I'm going to do is I'll go back to y equals, and I'm going to turn off y1. We'll just work with the one graph there. So there's that red graph. Now on A, so here's how this works. The up-down arrows will let me change from A to B to C to D. And the left-right arrows will increment or decrease those values by units of 1, okay? So if I go to D equals, I hit the left arrow on D, it changed to -1. Okay. Let me go over to, I think it works, it goes to the nearest. You can see how the graph's changing as I change these values. Let me put D back to 0 again. And let me now go up to B. And you could just enter a value if you like. I'm just going to enter 4. Now this window is not looking as good as it did before. I'll tell you what, let me go ahead and change A also. Let's change that to say -2.
Tom, when you change those like that, can you change them to a decimal or does it have to be an integer?
Sure, I could change A to say -2.5.
Okay.
There we go.
Okay.
And now I'm going to do a zoom decimal window. So I'll go down to zoom decimal. There we go. All right, maybe not the best window, but at least I'm seeing all 4 of the roots there. Again, I can use the left and right arrows to, I think, let's see. There we go. A is changing now. because I had to regraph.
Yep.
So and notice it's jumping by a full unit. Okay,
Yeah.
so if I start on a decimal number that's not an exact integer, it's just going to increment by 1. But I could change it to whatever value I like. And if I change, what would happen if I made a 000? So I'm going to go over to B, and I'll just put in 0 for it also. Boom. That's an interesting graph. So now this is a 000.
So I think this is something that's really important to show students is that it, and I used to tell mine, it's sort of, here we go with like bounce. It wiggles through x equals 0, kind of like a cubic, y equals x cubed does, as opposed to going like a singular x-intercept. It just goes straight through, like the one that we have at -1.5. And students need to graphically kind of begin. This is a little bit, we're getting a little deep here, but I think students need to begin to see these multiplicities of 3, like what shape that graph is taking as it crosses through that particular 0.
And the fact that it's an odd multiplicity, it actually does change sign at that 0. While if it's an even multiplicity, you'll get that, what we were calling kind of the bounce effect.
Yeah. I just think I love this. No, I just love this. I think the power of the graph here is so important to help their understandings of the zeros and the connection to the factors.
Tom, if I could, I want to add one other thing. One thing that Vicky mentioned earlier this evening is, you have to be careful about what this graph is really telling you. If you look close to 0 there, close to the origin, it certainly looks like this graph is a straight line, is a horizontal line. And so you have to take this visualization, this graph, along with the analytics to know really what's going on here, right? You can't just blindly think, oh, well, it must be a straight line from about, minus 0.25 to 0.25.
Yeah.
No, that's not correct. Even though
And
that's
actually,
what it looks like.
it brings up something else that students have a very bad habit of doing. When they can't find that complete graph, they have the habit of doing zoom fit, and they don't understand what zoom fit
Does, yeah.
the intentions of zoom fit. And I've seen some absolutely gosh awful graphs when students thought that they had what they needed, but they did a zoom fit.
And I didn't quite do what I wanted to do. I went down to -1, but I should have made the Y max
Tom,
smaller too.
I got so two comments. First of all, one, yes, Vicky, I love we need to maybe demonstrate or even talk about what does zoom fit actually do just from the functionality of the TI-84. So Tom, I'll let you think about how you want to say something about that. But before you do, the other question I did get a question about, is there a way to find points of inflections on the 84?
Yeah, I mean, it's a great question. It would be, there is in terms of calculus.
I was just going to say, the only way I could think about is, we need to maybe do some calculus to find that.
But. Right. So if we're staying within the context of pre-calculus, it would be, I'd have to think about what might be strategies for at least isolating or getting closing in on an inflection point.
I think
visually. But if I could use calculus, I could use a numerical derivative of a numerical derivative and try to find where that changes.
I think visually the students just need to be able to, in general, say it's got to be right in here somewhere. We would want a little better window, perhaps narrow in our X-min and X-max a tiny bit to kind of get that feeling, but they should be able to somewhat estimate where that concave down to concave up or vice versa is actually happening.
So,
So,
for example, here it appears somewhere between -1 and 0.
Mhm.
We've
Right.
got one inflection point, and that 0 of multiplicity 3 is it turns out to be another. In
Yeah,
fact,
and that was pretty
that's
clear.
right on. Yeah.
yeah, that's a good one. So, Tom, really quick, just on the on this image here, why don't you change the X min and max to something narrow, maybe a little more narrowed in.
Sure,
Maybe,
yeah.
maybe really narrow it in to something like I don't know what the zeros are.
Or -2 to +2, Tom.
So like yeah, there you go, -2 to +2. And
I might go just -2 to 1. Let's see
or
what
even
happens.
-2
Yeah.
to 1.
Okay.
Yeah, sure. And now
Here we go.
we'll see.
There we see.
Okay, so what Zoom Fit does, if I choose to use Zoom Fit, and you can go ahead and demonstrate
I'll
it
go
right
ahead and
here.
just scroll down till we find it.
If you scroll down till you find it.
What
Zoom
it does is
Fit,
it actually takes all of your X values and makes sure that they're all the Y values that go with those all show up on screen.
well, that's a really nice way of saying it.
Yeah.
Yeah, it makes sure that you can see the entire domain and associated range.
Range. All right, but that's the
But
key, Curtis, is the
yeah,
associated range with
With
that
that
domain.
domain.
All right, so
right.
I want you to do something different. I want you to do the good old Zoom standard that a lot of students use.
Okay. That would be number 6 down there.
Right.
That's our -10 to 10 in both directions.
Yeah. It is where a lot of students think they need to start. And then I don't know what's going to happen because we're really off our we're doing weird things here, but now do Zoom Fit. In other
Yeah,
words,
that's a
they
much
haven't taken into regard a domain restriction that will show us the features of the graph. They're just blindly, in my opinion, using Zoom Fit.
and from -10
Right.
to
And now
10.
it's going to look like this really flat graph
Mhm.
Yeah, yeah.
because
So
the scale is so large to hit that right-hand side endpoint, that really,
yeah. So they
So now it
lose.
almost looks like a quadratic.
It does. And they may believe it's a quadratic. So, I would like to caution both teachers and students, be very careful with Zoom Fit. It's not going to fix your errors if you're not too sure of what you're doing. It could get you into more trouble than it's worth. So,
In case point, let's just check our window and see what it had to do to the window to get
okay.
fit. And check out my
Oh
Y
my
max.
gosh. Yeah, that's pretty crazy. Well, look
1,000
at your Y min.
And that's because it had to go so high to pick up the Y value on probably my X min, I think, was the one that was that the one that was so big, or is it?
no, it's the X max. So
What
yeah,
X min?
slightly larger over there on that side. So
Notice it's just reaching the corner. That's not an accident. That's part of what Zoom Fit. If the extreme Y value is right at the end of occurs right at the end of my X domain, then I'm going to have a Y max or Y min that fits that too. All right.
so
Steve, I should probably, or unless there's anything else.
Yeah,
Moral
before
though
you
is, I think this transform app is incredibly powerful for this kind of explorations. Go ahead, Steve.
before you leave this problem, if you would have an opportunity just to show how to find the intersection between that F and -10
Sure.
on
Yeah,
the
let's
84.
go back to
So
And
you got
you got to get out of the
exit.
transform app and get back to
okay,
your
so to do that, let me go back to apps and I'll go down to transform. And it gives me the option to quit. And this is something that is worthwhile to remember, because if you're done using the transform app and you just want to do some regular graphing, you do need to kind of consciously quit the app. And this is just go back to it and pick this quit transform graphing. Then when you go back to y equals, you'll see that those special symbols
yeah.
left, the
That's
y1 and
good.
y2 are gone now. So I'm going to, our y2 now is not at all the same as it was at the beginning. So let me turn it off and go back to our original y1, which was the same function that Steve had. And let's see, I'm going to want a window that includes, let's see, well, my y min, it's got to be less than -10. So let me go down and say -15. And then I'll do my y max. I'll just make it 15.
Okay.
And let's just graph that now and see what we get. So our our positive 12.3 is still not on there. So I should probably go x min. Let me, oops, -5 to 15. That'll get everything on screen. So let's try graphing again. Should come up. Now I realize this is not a complete graph in the terms of us seeing the two turnarounds below the graph, but it is far enough down for us to use y2. I'm just going to make it equal to -10. Let me clear it first. -10. That'll give me that horizontal line that you had on your graphics page. There we go. And we see there's that nice 4 different spots where it crosses. Let me just do one of those.
You can just do one. That'd be great.
Yeah, just do the calculate menu again. And it looks like down at number 5. That looks good. Let's hit that. It says first curve, and I can see I'm on the blue one. So I'll say, yeah, that looks good. Second curve's the red one. There's not a whole lot of choices there. Let's see, which 0 do we want? If we want this one out here between 12 and 13, again, I could, excuse me, there is, it looks like there's a 0 between 12 and 13, but there's also a crossing point.
Correct. Yeah.
So let me go ahead and put in 12 for a guess. And there's the intersection values. The y value is no surprise. It's -10. It needed to be that for both functions. And there's that x value. And if you wanted to use that in a further calculation, if we quit from the graph and just pull up x, it should be that intersection x value. There it is. Now, if you want to go do some other things, you might want to store that value away for safekeeping, but it's accessible there. And I hope I didn't rush that too much, but it behaves very similar to the 0 functionality that we saw before.
Pretty cool.
All right, I'll stop a share there and turn it back to you, Steve.
Well, Curtis, we've run out of time.
Run us out of time here.
Can we go till midnight
that's all right.
tonight?
That's really okay. We got through some technology tips, and I think that was useful. We had several students on tonight. Hopefully they picked something up along with their fun chat and chatter in the chat box. So thank you, students, for joining. Thank you, teachers. I did put my email in the chat a minute ago, and I will put it in just one more time here in just a second if you're looking for that professional development hours. But you can email me at curtis@ti.com. And until next time, we will see you guys here in about a month. I believe it's October the 17th. Is that right? That is the next session. We'll continue our exploration in polynomials. We may bring back a couple of things, but I'll have these solutions posted sometime tomorrow.
Actually, we're doing rationals.
Oh, we're doing rationals next time. That's right.
Yeah.
That's terrific. And we will be doing a little bit on the rational functions. So stay rational. All right, everyone.
Thanks, Curtis.
Thank you.
Thank you.
Very good.
Bye.
All right, everyone.
You know, I